Lab 3 on black holes and orbits. So the table of contents, you got the introduction, we'll have the purpose of the lab, procedure, lab plan and coding, data analysis will be the results and discussion. The introduction. In part 1, the goal is to find the mass of the black hole. In order to find the mass of the black hole, use the gravitational force and circular motion. In part 2, you'll be finding the orbit of a spaceship so that it doesn't crash. It can't crash into the moon or the planet, and use gravitational force, circular motion. Yeah, so in part 1, the system is the star and the black hole, your surrounding, nothing else. Part 2, your system is the planet, the moon, and the spaceship, your surroundings, nothing else. And the computational model that we'll be using is GlowScript. So the physics principles that will be used in this lab are Newton's second law. We've been using this in the last 2 labs. It's the change of momentum is equal to the F net, and this gives us the velocity update formula as well. Another one that will be used is the parallel and perpendicular forces of F net. Those will be used in the first model. Then finally, we've got the universal gravitational force, which will be used in all of them. So the procedures for part 1. So in part 1, we'll use the starter code and change it to find the mass of the black hole. So this is the part 1 code. You got your initial conditions over here, your gravitational constant, mass of the star, your delta t, which is the time between each point. T equals 0, you'll initialize that, and then you do all this to calculate the velocity. So in order to find the mass of the black hole, you find your initial momentum and your final momentum. Use that to find your change of velocity or change of momentum. And that'll get you your dp/dt. And you can put your F net equal to that. Right here in this area, you're finding your parallel force of F net using that equation, which is given by right here. And to find the perpendicular, you just do dp/dt minus parallel force, and that'll give you your F net perpendicular right here. And then using all of those, you can calculate the mass of the black hole with the gravitational force constant, solving for mass. And I also added here a part so that you can calculate the average of all the masses, because you're getting a bunch of masses throughout this. So without that, you wouldn't have one number. And of course, down here is the scaling of the different arrows, so that it looks proper. So these are the results. You can see this motion right here, and you'll see your forces. Magenta is the parallel, cyan is perpendicular, orange is the net one. And you'll see it increase as it got closer there, because the force is increasing the closer you are to the black hole. All right, part 1, results and discussion. So as I said earlier, we had many different mass values, so they had to be averaged together. So the final estimated mass was this right here, very big number. And a big important thing about this is in this case, you think the force of gravity would be the same as your change of momentum. However, they're not, because your dp/dt is not an instantaneous, while your force of gravity is instantaneous. So it's dependent on your position. Part 2 procedures, you're going to use the starter code and modify it to find the initial velocity that allows the spaceship to orbit both the moon and the planet. So this is your starter code, your same initial conditions that were given, and I increased the time a little bit to show like more of the orbit. So basically what you do here is you're finding all the different gravitational forces from like the planet on the moon, ship on the moon, and you get the F net, and then you get the F net of the ship. And you're going to use all that. You're going to use your velocity update, your position update, your velocity update, your position update, and that will give you the video that you're about to see, which is the final video. So this is the final result. As you can see, with the dips in there, it's orbiting around the moon here, as well as orbiting around the planet here. And like I said, I got the final speed to be this right here. It took a lot of process and error. That was the best way that I could find to show the best orbit. Potential sources of error. The black hole calculations were an average, so those aren't going to be fully accurate. And also, this whole thing is a model, so it does not account truly for the real world. What if um, you would include all the different gravitational forces on each object exerts on the other, and there would be dominant interactions as larger masses and closer distance would have stronger forces.